So we are asked to sketch a PV and TS diagram for the cycle, determine the ratio of compression work to the expansion work, and determine the cycle thermal efficiency. So we're going to start by drawing our TS diagram and PV diagram. So we draw our axis. This will be PV, and this will be TS. And let's follow our instructions. We're being told that we want to choose a constant volume heat addition. So constant volume will be just recorded as a vertical line, right? We know that this number is 100, and this will be 700 kilopascal. In the TS diagram, we start with, let me just make this a little bit clearer. We start with 300 Kelvin, and we start with a constant volume, which is similar to this. Okay, so this is our first process. The second process says that we have an isothermal expansion until we get V3 equal to 7 times V2. So in isothermal expansion, we'll look in the TS diagram as a horizontal line, and in the PV, the expansion will require volume to increase, pressure to decrease. We're going to do a line like this. And at the end, we have constant heat rejection, constant pressure heat rejection. So that means that this line, imagine that this is a constant pressure line, right? And this line will have a different slope to the original state. So we should recognize that we have a fixed mass, and because we have a fixed mass and we have air as an ideal gas, PV equal to, let me change this to just to emphasize that this is lowercase v. It's constant, right? Because we have the same mass. So first process, we can P1 V1 T1 but you know pressure 1 and 2 is the same, so we can just cancel this and solve for T2. So T2 will be T1 times pressure to pressure 1. We know this, we have all the data, so this is 300 Kelvin times P2 is 700, P1 is 100 kilopascal. Let's cancel. So we have T2 equals 2,100. Now process 2 to 3. We need to compute the work out. So we will start with our general expression. This is the work for a mechanical system. and we need to find an expression of p as a function of p, and we have it here. We know that PV equals RT, so we can have P equals RTS divided by V. So we have pressure in function of volume. We can just substitute here. And since R and T are constant, we can take it out of the integral and have minus RT integral of dV over volume, and this integral goes from 2 to 3. So doing the integral, we know that this will be minus RT times the natural logarithm of V3 by V2, but we don't have these values. But we remember that seven times V2 is equal to V3. So if we substitute the numbers, R is 0.287. Let me write a little bit nicer here. Kilojoules per kilogram Kelvin times G is constant because it's an isothermal, and we know that it's 2010. Times the natural logarithm of 7. Kelvin cancel, and the result is 1172.8 kilojoules per Kelvin. Sorry, per kilogram. We have a negative sign, and remember, I'm just going to do this in different color. But remember, for any system that we are talking, everything that goes in is positive. Anything that goes out is negative. So this just confirms that we have our work going out. So, but we know that the work and heat doesn't have any sign, so we have work 2 to 3 equals 1172.3 kilojoules per kilogram. This is an important result, so we are just gonna underline it. Next, we're gonna study process 3 to 1. So for process 3 to 1, we follow the same. We know this work, so we need to start with our general expression, and again we need to find out expression that says everything in terms of pressure, but we remember that pressure is constant, so we can just take it out of the integral. So this will be P dV from 3 to 1. If we perform the integral, we know that this will be minus P V1 minus V3. but we don't know either V3 or V1, so we are gonna invoke again that PV equals RT. So this will be RT1 minus RT3. R is constant, so we have 2.87 kilojoules per kilogram Kelvin times T1 is 300 minus T3. Sorry, we have the minus sign here, minus sign here, minus 2100 Kelvin. So our Kelvin cancel, and at the end we will have 516.6 kilojoules per kilogram. Notice that it's positive, and that's consistent that this is working. So okay, this is important to underline. We are now ready to compute the bubble ratio, and this is what percentage of the total workout needs to be introduced for this cycle to function. So this will be 500.16 kilojoules per kilogram divided by 1172.8 kilojoules per kilogram. So these units cancel. This bubble ratio is an dimensional number, and we equal to 0.4405. That means that 44% of the work that I'm getting in the expansion portion needs to be introduced to the cycle in the compression. So this cycle works. Finally, we need to compute efficiency, and we know that efficiency is a net work divided by Q in. Net work is very straightforward, since it's work out minus work in. Remember that we need to invest 44% of the workout as into the work, so we can have this cycle running. So this will be 1172.8 minus 516.6, and this is equal to 656.8 kilojoules per kilogram. But we are missing Q in. Now, let's go back just one page and see that when we have in this expansion, what we expect with expansion is the temperature to drop. Nevertheless, we have the same temperature. So that means that we are having some heat here. So let me just write this. We have Q in, we should have some Q in here in order to keep the same temperature. So because of that, we are gonna perform an analysis to find Q in, total Q in will be from 1 to 3. So applying first law analysis will be Q in minus Q out. We start from the general expression. We know that we don't have any Q out, plus work in minus work out equal U3 minus U1. We don't have any work in. The first part of constant volume. Second, and we only have workout. So solving this will be Q in equal U3 minus U1 plus workout. And this difference in internal energy is CV T3 minus T1 plus workout. If we substitute, CB is 0.718 kilojoules per kilogram times 2100 minus 300 plus the workout that we already computed, which is 172.8. This Q in total will be 2465.2 kilojoules per kilogram. And so the efficiency will be the network, which is, sorry, the typo, 656.8 divided by 2465.2, and this is 0.2662. So the efficiency of the cycle 26.62%. Okay, so you can see that we can analyze any cycle using these considerations. We need to just do either first law or define the process that we have in each state. Next problem, we're gonna solve an example with variable specific heats. You can see here that we were asked to have constant properties. So this is the constant specific heat values. Okay, so we are going to solve now problem 915. Change from the past one is that we have 4 processes instead of 3, but most important is that we have variable specific heats, so we're going to use table A17. Okay, so we have an isotropic compression, then a constant volume heat addition, isotropic expansion, and constant pressure heat rejection. We're asked to find out the PV and TS diagram, compute the network output per unit mass, and of course our efficiency. If we are also asked to build ITES, to write the ITES program. I will let this for you to do it, and later on I will send you the solution to this program. Okay, so let's start. I'm gonna change the color of my ink, and and we're gonna start by drawing our TS diagram and PV diagram. So this is P, V, and TS. So let's start with the PV. We know that we start with the compression. It takes from 1 to 2. We need this pressure is 100. And this pressure is 600. Then we have a constant volume, so this is a vertical line. And then we have an isotropic expansion. This should be a curve, so I'm going to change this a little bit just to show that it is a curve. and at the end we have a constant pressure heat rejection. So if we draw the interactions, this is Q in, this is Q out. Here we draw the same for the TS diagram. We're going to start by recognizing that the compression is an isentropic, so it's a vertical line. Then we'll have constant volume heat addition. Then we have a second vertical line, which is our isentropic expansion. Then we have a constant volume. Just change this a little bit, show that they don't have the same slope. For this diagram, we know that this is 295 and this T3 is 1500. So we're going to start with the basic definition that efficiency is net work divided by Q in. And in this case, we're going to compute Q net work as the difference between Q in and Q out. Okay. So we need to use variable specific heat, so we're going to use table A17. So we would like to understand how to get Q in and Q out. So process for Q in is process 2 to 3. We apply first law. We notice Q in plus minus Q out plus work in minus work out equal U3, which is the end, minus U1. Remember that this is a closed system, so we don't have any work in or out because it's a constant volume. We don't have any Q out, we only have Q in. That's the process that we're analyzing. So sorry, this is U2. So in these two cases, you can get U3, but we don't know U2. U3, we go to our table at 15. We can see that U3 is 1205. So we know U3 is 1205.41, and PL3 is 601.9. That's kilojoules per kilogram, and this has no dimensions. So how do we get U2? Well, we know that process 1 to 2 is isentropic. So again, a table A17, we can get the data that we need. Okay, table A17, we can check that for 295 Kelvin, PR1 equals 1.3068, and since process 1 to 2 is isentropic, we can use this expression, PR2 divided by PR1 equal to P2 P1. Now we are using relative pressure because we know both datas of pressure, but the number. So solving for PR2, we have PR1 times P2 over P1, and this is 1.3068 times 600 over 100, and this is 7.841. Now, looking at table A17 again, we can find that PR2 with PR2 we have that temperature is very close to 590, and that will make U2 equal to 352.08 kilojoules per kilogram. So we have U3, we have U2, we can compute Q in already. So we have 1205.41 kilojoules per kilogram minus 352.08. This is 453.33. Let me write it again. Well, I think that's clear. No, let me do it again. You mentioned that sometimes you didn't get my handwriting, so let's do it right. So this is 853.33 kilojoules per kilogram, and this is part of what we need. Now we need Q out. But for Q out, we have to process 41. On 41, we start with Q in minus Q out plus work in minus work out equal U1, which is the final state, minus U4. We can cancel Q in. We can cancel work out, but you should recognize that we are having a compression here. Going from 4 to 1, we have a compression because we're reducing the pressure. So we have some work in. And this work in we're taking pressure out since it's a constant pressure process. At the end will be minus P before V1 minus before, or P before minus P V1. This pressure we can mention P1 is the same. So if we substitute here and solve for Q out, we'll have, we'll have P before minus P V1, and we pass this the other side, so it will be plus U4 minus U1. Now we are going to gather these together. Once in P V4 plus U4 minus P V1 plus U1. We are factorizing this minus sign, and you may recognize this as enthalpy 4 from your fluid mechanics class or your thermal 1 class. So at the end, Q out equals H4 minus H1, and H1 we can get it from table A17. And H1 will be 295.17 kilojoules per kilogram, but we don't know H4. We remember that process 3 to 4 is an isentropic process. So we call the same PR4 divided by PR3 equal P4 divided by P3. Now PR4 is PR3 times P4 over P3, and PR3 we can get it 601.9 times P4 is 100, 600 is PR3, and this gives us 32.79. It's not tabulated, but we can interpolate. So what we're gonna do is we're gonna interpolate between these two values. 32.02 and 33.72. Add these values. H is 734.82 kilojoules per kilogram, and at this value is 745.62. So we want to interpolate it between these two values to get 32. 0.79. So by linear interpolation we can get to this value. It should be between these two, and we get 739.68. So Q out will be difference between these two, 739.68 that we just got, minus 295.17. This is 444.51 kilojoules per kilogram. Now we can get a network, and network will be 800 and 53.33 minus 444.51, so that will be 48.82. So this is one of the results that we are looking for. The specific work, 408.32 kilojoules per kilogram. And finally, the efficiency will be this network 0.32 divided by Q in, and this Q in is 853.33, and this relation is 0.4791. So in terms of percentage, we can say that this is 47.91% for the thermal efficiency. Okay, well, that's it. And next we're going to start with the Otto cycle. Thank you.